idea of freezing light, slowing it down to an almost complete halt, sound like something out of the science fiction. However, a team of Italian research at the National Research Council of Italy, CNR Nanotech, at the University of Pavia have successfully done just that. They have created a new quantum state where light behaves like a supersolid, a form of a matter that simultaneously flows like a liquid and maintains a structure from like a solid. To fully grasp this remarkable achievement, we must analyze how the scientists conducted their experiments, what materials did they use, what were the conditions required, and how did they measure the effect. Let's break it all down step by step. So step 1. Choosing the right medium for light manipulation. To manipulate light in such an extreme way, scientists needed a special medium that could slow it down and force it into a structured pattern. This wasn't an ordinary optical material like glass or fiber optics. Instead, they used a Bose-Einstein condensate (BEC) of ultra-cold atoms. So why a Bose-Einstein condensate? A BEC, or you can say Bose-Einstein condensate, is an exotic state of matter where particles behave as a single quantum entity rather than as an individual atom. In simple terms, it creates an environment where a strange quantum effect becomes dominant, allowing light to interact with the matter in a way that's not possible in regular conditions. In this experiment, the scientists used a carefully prepared gas of rubidium atom which was cooled down to near absolute zero, minus 273.15 degrees centigrade or 0 Kelvin. This extreme cold forced the atoms to enter a quantum state where their wave function overlapped, essentially making them behave as one giant superatoms. With the BEC medium prepared, the next step was to introduce light into the system in a way that would allow it to be controlled. Instead of simply shining a laser through the material, the researchers used a technique called electromagnetically induced transparency, EIT. How electromagnetically induced transparency works? EIT is a quantum optic techniques that allows scientists to manipulate the way light moves through the materials. Normally, if you shine a laser into the dense atom, absorb the scattered light, making it impossible for it to pass through. But the EIT, another control laser beam, is used to alter the atomic energy level in such a way that the gas becomes transparent to a third probe beam. This technique allowed researchers to trap the light inside the rubidium BEC without it escaping while still keeping it in an active state where its properties could be manipulated, creating supersolidity in light. Now came the most critical and delicate part of the experiment, making the trapped light behave like a supersolid. This required fine-tuning and interaction between the light and the BEC atoms, manipulating the light-matter interaction. To force the light into a supersolid phase, the scientists introduced controlled interaction between the photons and the ultra-cold atoms. They did this by adjusting the laser intensities by precisely tuning the power of control and probe lasers. They could alter the way light waves interfere with each other inside the BEC using optical lattice. An optical lattice is a grid-like a pattern of laser light that creates potential wells where atoms and photons can be trapped. The researchers used this technique to structure the light into an ordered yet fluid-like formation, coupling photons to atomic excitations. This means that photons were not just freely moving inside the medium, they were partially converted into the polaritons, quasi-particles that are mixed of light and matter. These interactions force the light to organize itself into a rigid patterns while still allowing wave-like movement, thus achieving a supersolid state. After creating the supersolid state of light, the next challenge was to confirm and measure it. Scientists needed precise detection method to prove that light was behaving both as a solid and liquid simultaneously. How did they measure the effect? Interferometry. The researchers used a highly sensitive laser interferometer to detect small fluctuations in the light structures. If light was truly a supersolid, they expected to see both periodic patterns, solid behavior, and fluid-like oscillations, liquid behavior. Photons correlation measurement. By analyzing the way individual photons interacted inside the medium, they could observe whether light was behaving like a single quantum state. Microscopic imaging of the BEC. Since the light was strongly coupled to the atoms, they also imaged the atomic cloud using a high-resolution cameras to visualize how the photons were distributed. The result confirmed what they were expecting. The trapped light formed an outer pattern like a solid, while still flowing like a liquid at the microscopic level. So what is the thing? Now the scientists have successfully created a supersolid state of matter. So what's next? The discovery could open doors for the major advancement in technology, including quantum computing. Light-based quantum processors could become more stable and efficient, enabling the next generation of computing. Second, secure optical communication. Controlling light at such a deep quantum level could lead breakthrough in hack-proof communication networks. Number 3, energy-efficient optical storage. Future data storage system might rely on the controlled light waves instead of electricity, making them faster and more efficient. The experiment conducted by Italian scientists marked a groundbreaking step in our understanding of light and quantum physics. By carefully preparing a Bose condensate, injecting light using electromagnetically induced transparency and fine-tuning photon atom reduction, they created an entirely new state of matter, supersolid light. This discovery is not just a scientific curiosity, it has real potential to revolutionize quantum technology, impacting everything from computing to communication and energy storage. Science continues to push the boundaries of what's possible, and with research like this, we may soon unlock entirely new ways to harness the power of light. If you found this fascinating, stay tuned for more deep dives into the future of quantum physics and cutting-edge technologies.